Okay, what I want to look at here is the diffraction formula for Young's slits. Now, you probably already know, and I'll just try and go through this a little bit, that this is the formula where we use approximations, and we just want to have a little look at that. So we've got the wave coming through here, hits these lines where we've got these two slits, and it can pass through where the dots are. So that's basically a slit that the wave passed through. We have a screen some distance down here. We'll draw it in here. And so at a point on that screen, we'll call it a point up here, the waves which hit the slits in phase have then travelled to the screen, and we're looking at a point there. And what we're saying is that if that's a fringe, or bright fringe due to constructive interference, then the path difference between these two lengths is in fact one wavelength. And what we do is we have a look at this here, over here, and we go, well, if we draw it that so it's a right triangle, and D is the distance between the slits, then the angle, right, so if we were to look at the angle that we have here, the angle that would be, let me draw it, I haven't drawn it in, but the angle that angle there, theta, doesn't look like a very good theta, does it? But that angle between the horizontal line and that line, theta, is going to be the same as the theta here, the angle between the vertical that I put in, and the path difference is this bit here. So what we're basically saying is that D times the sine of theta equals the path difference, which in our case is n wavelengths. Looks like the diffraction formula for mini slits when you get there. But we have a problem. And the problem was, yeah, that works if these lines are parallel, but they are not, are they? So we have an approximation there. And our approximation is, we need that, for this to work, this screen has to be a long way away, so that that whole parallel issue isn't such a big issue. So screen needs to be distant, in comparison with the slit size. So that's the first approximation we do, and that takes care of this parallel thing. We're saying, oh, well, that's going to be a really small difference if it's a real long way away. Then we've got the issue of, okay, if that's theta, and we've said this distance here is x, and the distance from the slits to the screen is L, then we can say that x over L is equal to the tan of theta, right? We definitely can say that. Perfectly okay. And what we in physics say also is that the tan of theta is equal to the sine, approximately equal to the sine of theta, which is approximately equal to theta, for small angles. So what we're basically saying is, yeah, this works for small angles. Alright, and you'll have been shown this little, you know, you shine your laser through your little Young slits, the little slits, yeah, usually about 0.1 millimeter apart or something like that, and you get this really quite small little pattern of bright, dark, bright, and it's the bright one that we're trying to get. Then that first fringe, then we'll have a second fringe, that sort of thing. Hopefully your physics teacher showed you that, and that's between two slits. If you can measure the distance and get the angle and all that, then yeah, you can work back to find the separation for D. But I didn't quite explain, since these guys are the same for small angles, what we do is we substitute in D x over L, alright, because we just want sine theta, and we've said that's equal to x over L, it's equal to n wavelengths, and we end up with that formula. And it's based on these two approximations. Screen needs to be distant, and the angles need to be small. When you look at these tan theta, sine theta, doesn't matter whether you use degrees, but for theta to be the same, we'd have to have it in radians, alright? Okay.